right, so we're going to get into chapter 12, which is kinetics. Uh, so like a little outlier chapter in a sense. And then we'll get into, after this chapter, really the main topic of the class, which is equilibrium. But first, before we do, we're going to talk about kinetics. And the idea of kinetics is it really tells us how fast a reaction takes place. It can also tell us, obviously, how slow a reaction takes place. And that in combination with thermodynamics, which you probably learned a little bit about in Chem 50 when you did all the delta H and the change in enthalpy. We will do the rest of thermodynamics later on in the semester, and we'll talk about things like entropy and Gibbs free energy. Thermodynamics, oftentimes, as we will talk about, deals with the idea of whether or not a reaction will take place. And we will hear the word spontaneous used a lot. And sometimes people have a misunderstanding of what the word spontaneous means. So a lot of times when people hear, for example, a reaction is spontaneous, in their head they think it like happens super fast, right? It's like spontaneous happens very fast. But in this context, when we talk about it in sort of the thermodynamic aspect of it, what it means when a reaction is spontaneous, it basically just means that under those particular conditions, that reaction will take place. Now, that reaction could be really fast, that reaction could be really slow, but you have everything that is necessary for that reaction to take place without any type of outside influence to allow that reaction to occur. And that is what really spontaneous means. How fast or slow the reaction will take place is really what kinetics sort of studies. So that's what we study with kinetics to figure out how fast or slow. Again, we'll talk about later on as well when we get into the thermodynamics in a later chapter, which I think is 16, if I'm not mistaken, or 17. But again, you could have a spontaneous reaction that takes all day, a very, very long time to actually go to completion. And you could have a spontaneous reaction that happens really, really fast as well. So when we talk about kinetics and rates, we oftentimes think about reaction rates. And reaction rates in our context usually involves some type of change over time, right? So like when you're driving, you go so many miles per hour, right? That's basically what that means when you're doing 75 miles per hour. If you lock it in, when 1 hour, you should hit 75 miles is basically the distance that you should travel in that particular period of time. So for us, what we typically look at is concentration versus time. So how the concentration of reactants or products are changing with time. Obviously, we talked about it last time, but big M, right, is our friend molarity. I'll get that M out there. Molarity, moles per liter. So in this case, when we look at units of molarity over seconds, we're looking at how the molarity or the concentration of a reactor or product is changing as a factor there of time. Now, when we look at a reaction such as this, we see a couple of things, and we could write these sort of relationships as these sort of changes over time. We could say, for example, here that A will, the rate of it will be minus the change in the concentration of A over the change in time. A reminder as well that when you do see brackets around something, it does mean concentration. And pretty much most of the time, that is going to be molarity, is really what we're looking at when we see that delta there, the little triangle, which is the delta means change. So the change in time, I'm sorry, change of concentration versus change time. Now, as this reaction occurs, this is a one-way arrow street. When this reaction happens, would we expect the concentration of A in this particular case, should it get smaller or should it get larger? Should get smaller, right? Because on the left-hand side here, I think they still call those reactants, right? On the other side are some products, right? So in order to make our products in this reaction, our reactants has to come together to form the products. The result of that is we should see a decrease in the amount of reactants. At the same time, we should then start to see an increase in the amount of products that are going to be made. And in this expression, which is sometimes referred to as the rate expression, that is why we actually have a negative here. So we do have a negative here for our reactants, and that is because as the reaction is taking place, our reactants are actually decreasing their concentration with time. We could also write a rate expression for B, which is our products, which, as I just mentioned, we should expect to be increasing with time. And as you can see here, it's basically kind of the same deal. The only difference is we do not have the negative here. So no negative here because it's increasing with time. The reason for that is when you calculate the rate, this number here, it should always be a positive number. Yeah, so you should always end up with a positive number for the average rate of a reaction. Now, why do we need the negative in the first one and not in the second? As you may know, perhaps that when you calculate the change in something, like the change in concentration of A, you would take the final concentration of A minus the initial concentration of A, right? So you take final minus initial. Now, if we just think about this reaction of A going to B, and let's say at the beginning, initially, we had 5 molar of this guy, right? And at the end, initially, we had nothing here. At the end of the reaction, we're going to have less of it, right? So 2 molar, maybe we have 3 molar that's made here in these made up numbers. So when I go to calculate something like the change in the concentration of A, in this case, it would be 2 molar minus 5 molar, and that's going to yield me a negative 3 molar, and that's going to yield me a negative number that I'm going to get always in this case because it's decreasing with time. That negative that I get by the subtraction is canceled out by this negative that's in front, and that's going to turn my rate back into a positive number, which is what I do need in this case. Now, for B, in case of B, you do not need that because when you do the change in the concentration of B, it is going to actually end up with a positive number. So if we did the change in the concentration of B in this case, taking our final, which is 3 molar, minus our initial, which is 0 molar, that yields me a positive number here, which means that again is going to give me a positive number for our rate. So when you write the rate expression, because the reactants are decreasing with time, we do need that negative in front to turn our average rate of the reaction into a positive number. Any questions on that there? If we were looking, for example, at an individual species here, so if we were looking at A specifically, and we wanted to know how A was changing with time, we actually will end up with a negative number because it's decreasing over time. So when you're looking at an individual reactant and trying to figure out basically its rate, you do end up with a negative number because it's decreasing with time, and you would end up with a positive number if you're just looking at like B by itself, the product in that case. But when you're looking at the overall reaction as a whole, that average rate should end up being a positive number always. So when we look at these, there are a couple of ways that we could kind of follow the rate of a reaction. And a very common way is we look at graphs and we do some absorbance type values, which we'll do in a later experiment. But as you can see here, as this reaction begins at kind of time 0 here, we pretty much have all of A, which are represented by these black circles here. And we can see we have no red circles in there, so we obviously have no products to begin with. As the reaction starts to proceed with time, we do start to see some red circles coming in, and the number of black circles are decreasing. And you can see as time continues, we are mostly now red circles and products being formed at the end of the reaction. Graphically speaking, we can see that in our graph. At the very beginning of the reaction, we have pretty much all reactant molecules. We have no product molecules. As we start making our product molecules, we're going to be using up our reactants, and we will see a decrease in those and an increase in our product molecules as we start making them. Now, one of the common ways that we can do these type of experiments is if you have some type of experiment where either a reactant or maybe a product makes some type of color, like here with bromine, it's kind of this orangish reddish type color. And that's over here, basically that kind of reddish orange color. And on the product side, these are all pretty much colorless. Yeah. So you can see as time goes on, we're starting to convert some of those reactants, which have some type of color, and it starts to decrease, and we're replacing them with products that are colorless in this case. That's really good for doing some type of colorimetry, some type of spec 20 type of deal. And when you do that, as you may know, you take a light source that shines a wavelength of light or a photon of light at a specific wavelength. It goes through your sample to the detector, and you measure one of two things, either the absorbance of the solution, or most people don't do these days, but percent transmittance is the other thing that you can measure in this particular case. Now, when you do this, the amount of absorbance that you get for your solution is directly related to the concentration, which is directly related to probably the color of the solution. So if you have something that's very concentrated, you're going to have a pretty good color. That's going to absorb a lot of the light that's coming in. You're going to get some good absorbance values. As it gets, in this particular example here, to a more colorless, the light's just going to sell through and not get absorbed by the solution. You're going to start to see your absorbance values start to decrease in this case. As you know, you typically set it to the wavelength. By the way, the color that we see in the beaker there on the left is actually the complementary color to the light that's being absorbed, say, by the machine. That's why if we were doing this experiment, we wouldn't set the wavelength to kind of the reddish orange color of the visible spectrum. We would set it to the complementary color to that in terms of its wavelength. So if you had like a really dark red, you would probably be setting it more in the bluish green area of the spectrum, as it is the complementary color to what we see as being absorbed. How do you know what to set it to? You usually get this sort of calibration type curve where it takes usually, for example, maybe your darkest solution and it runs the absorbance value at multiple wavelengths and it prints out something like this. And you will do this in some of the experiments that we do. You'll get this sort of calibration curve that will happen. And typically you want to pick the maximum wavelength at where it absorbs. The reason for that is that gives you all of this in terms of absorbance values that your samples will probably not go off the scale. If you chose a wavelength way out here, you got about that much of absorbance ability there, which means most of your samples are going to definitely be off the scale and not going to get readings and stuff like that. So that's why this is usually the first sort of step that you do when you do some type of technique like this. This is also all related to our friend Beer's law. A is equal to BC. That is the absorbance. That is Beer's constant, which we use when we graph. And C is the concentration, right? So by getting the absorbance of the solution, you could also figure out Beer's constant. You can figure out the concentration of your samples that you're running. You can even use the other version of Beer's law, which is something like that. That's absorbance. That's the molar absorptivity coefficient. That's the path length, and that's the concentration. So sometimes these are comboed. A lot of times here at this school, we just kind of roll with this version of Beer's law, and you could graph it. So this is a very, very common sort of procedure to run kinetics experiments. And like I said, all you need is something in the reaction to have some type of color to be able to do this. This type of technique would be completely useless if everybody was colorless, because there would be no absorption of anything because there's no color for it to basically absorb. The light can't be absorbed by it. So in this case, if we were doing this reaction, the change in the concentration of Br2 is proportional to the change in absorbance. That's the proportional symbol. And again, as that solution gets more colorless, the absorption is going to drop. And that means we have less and less of the Br2, as that is basically the thing causing the color that we see. Now, let's talk about a couple of types of rates that we sort of look at. And most of the time when we're doing kinetics, we do look at the average rate, which is basically the change in the concentration over the change in time, kind of your final minus your initial. There is also the instantaneous rate, which is a rate for a specific period of time. So you could think of it like this: if you're driving here to Arizona, maybe to go spring training this weekend, and maybe you're doing an average rate of, 75 miles per hour, right? But there probably will be pockets where maybe you're doing 80, 85, hopefully not 90 or 95, or a nice safe 45 there on the right hand shoulder of the road. So for periods of time, you're not traveling your entire trip at that constant rate, right? So, as we know, we hit traffic and all of a sudden we're not traveling very fast at all, right? Then maybe traffic opens, right? You get the 2-lane highway, the truck, gets into an accident across the 2 lanes in the middle of the desert, and your last off ramp's like 40 miles behind it. I know this sounds like a personal experience, and it is, just so you know. If you ever driven to Arizona, you get past Blythe, right? And then your next civilization is Courtside, which is like a 20-minute trip. One time we were driving in and we were, should we stop in Blythe? Nah, it's only like 20 minutes to, I know, Courtside. A Walmart truck caught on fire and jackknifed into the hill and went across both lanes of traffic. People were just parked for a long, long time playing like, baseball on the freeway until they cleaned it up. And about, an hour or so later, you were really regretting probably not stopping there at the Blythe before you pass. So stop if you need to. You never know what's around the turn. Check your traffic app before you go too far. All right, well, back to my trip here. We are talking about our average rate. But again, as you're traveling, you can have periods where maybe you're not traveling overall at that same rate. But if you average out your entire trip from beginning to end, um, you probably maybe traveled at a certain rate. And that's what happens with reactions as well. As the reaction is progressing, it may be occurring faster at certain points. It may slow up. If you just think about it, right, what we need for this reaction to basically take place is we need our reactant molecules basically to um, react with each other. So at the very beginning of this reaction, we have a lot of reactant molecules available to react, right? So they don't have to go hunt around to find somebody to react with. They're going to be able to kind of find somebody to react it really quickly. So at the beginning of the reaction, you would probably expect a pretty good rate of the forward reaction here to happening because there's just a lot of availability of reactant molecules to react with one another. As those reactant molecules are converted into products, the amount of reactive molecules start to decrease, which now means it might take a little bit longer for people, right, to kind of come in contact with each other in terms of our reactants to start making products. So your reaction rate may slow down for a period of time, right? And again, as you start averaging, you may also see a pretty big jump in product formation at the beginning, right? Because those reactants can find each other. But as everybody gets a little bit smaller on the reactant side, maybe the products aren't forming as fast and they start to slow down as the reaction takes place. So during periods of time, we can have an instantaneous rate. You could calculate the instantaneous rate by taking the slope of the tangent of a line such as this, where you kind of find 2 points, draw a line, and then take the slope of that line as best you can. We won't do too much of that, but that's essentially how you do it. And you can cut that instantaneous rate there for that specific period of time. But again, if we average this graph out from beginning to end, we will have perhaps an average rate of the overall reaction. And in some cases, that average rate will be how reactants are changing with time, and it may not be exactly the same as how every reactant or product is changing with time. Yeah. Yeah, so the idea is like you have like you're like, okay, like I know these 2 points. It's obviously not a straight line what we have, right? But we have these 2 points. But I want to kind of figure out, that this period of time, sort of, you want to take as best straight line as you can between those 2 points off of the one that's curving, and then you want to take the slope of that one, and that will give you that'll allow you to calculate, for example, what the rate might be for like that like 20-second window or something like that. By the way, this chapter does have a lot of graphs in it, and sometimes to answer questions like homework questions, you may have to lay up like an Excel graph or something like that to basically be able to answer the question out of the book. So definitely in this chapter, kinetics is all about graphs, and you'll get the hang of it as we do some experiments. But there's definitely going to be some homework problems where you got to kind of make a graph of some of the information that's given to you to be able to kind of answer the homework problem, stuff like that. All right. So if we look at this, some data from this particular experiment, and just to look at some of the experiments, what we see is a couple of things. First off, we could see that at different time periods, the sort of initial rates for that particular period is changing as the time is changing. And that's what we were just talking about, during the period of the overall reaction, things could be reacting faster, slower, and, kind of moving around. But there is a relationship that we have in these type of reactions and kinetic reactions where we do get a sort of a constant relationship of how it is changing. And for this particular reaction, we could have something like the rate is equal to K times the concentration of Br2. This whole thing here is sometimes referred to as a rate law. And more specifically, this little guy here, which is actually a lowercase k and not a capital K, because capital K is actually the equilibrium constant that we're going to talk a lot about. So it is a lowercase k. That is what is known as the rate constant. And that is the relationship that we do see here in this column of the graph that gives us a constant relationship of how fast this reaction is sort of taking place. So you can kind of think of the rate constant as, you know, having an effect on how fast a reaction will take place. If you just think about it logically, mathematically, if I want to calculate my rate and this number is a really large number and I multiply it by this number, I'm probably going to get a pretty good number there for the rate, right? I can get a large number. Vice versa, if this is a really small number, when I multiply it by this number, I'm going to probably get a smaller number for the overall rate. So sort of the value of the rate constant will kind of give you an indication sometimes of how fast or slow this reaction may be taking place. And it is a constant sort of value. As you can see in this table here, is pretty much for this one, 3.5 times 10 to the minus 3 molar reciprocal seconds. Now, what happens if you do have a reaction where maybe it does not have color? How can you maybe do a kinetics sort of experiment? Well, for example, if you have something like this one here, which is the decomposition of hydrogen peroxide, it will make water and oxygen gas. Now, since it does make oxygen gas, everything here is pretty much colorless. I believe they just put some color in there so you can actually see there is something in the flask, I think. But as this reaction takes place, it's going to produce the oxygen gas. And when we talk about gases, we oftentimes talk about pressure. And dare I say that's our throwback there. That call that the ideal gas law, I think, still. Yeah. It's been a while, but I think. And if you use the ideal gas law, you remember hopefully that things need to be in specific units. Pressure there needs to be in atmospheres, right? Volume needs to be in liters. We got there P equals N is moles. Moles. R is a gas constant, 0.08206 liters atmosphere Kelvin mole. Or maybe they teach nowadays 0.0821 a lot, I imagine. Temperature is in Kelvin, right? So there are specific units for the ideal gas law. And you may be asking, like, how can we use the ideal gas law to figure out how the concentration or something of this gas is changing? If we take the ideal gas law and actually solve for N divided by V, that means it will equal P over RT. That's important because N in this equation is moles, right? And V is liters. And moles over liters is molarity. Yeah. So if you had a reaction like this and you wanted to sort of figure out how the concentration of the gas is changing, frankly, all you would have to follow is how the pressure is changing, as R is a gas constant, and you're probably going to do this experiment at a similar temperature all the way through. That will basically be the same. So by following the change in pressure, you're able to figure out how the concentration of O2 is changing with time. How do we know it is O2 in this case? O2 is the only gas in this reaction, right? So If we do not produce any O2, we will not have any pressure. And if we don't have any pressure, then we obviously didn't make any products in this particular case. We start to see the pressure go up. That means we are making O2, and we should be making H2O as well as a result of this reaction happening. So if you follow the change in pressure over the change in time, again, these guys are going to be constants in this situation. That will allow you to get to your sort of kinetics information of how the concentration of O2 is changing with time. And in this case, it probably should be a positive sort of deal, as it is a product and should be increasing with time. Any questions on that there? All right. Now, we can't forget everybody's other favorite thing, which is stoichiometry, right? So whenever we have an equation, we have the coefficients in the equation, and that is the mole to mole relationship, right? Or the stoichiometry. And from this particular equation, that tells us for every 2 moles of A I toss in there, I'm going to get 1 mole of B out. And that is the stoichiometry relationship. So when we're dealing with reaction rates and how fast or slow reaction is taking place, we do have to take into account the stoichiometry of the reaction to give us the right calculation, basically. Now, there is a way that you could actually take into account the stoichiometry of the reaction along with doing sort of the kinetics calculation all together. And that is by taking 1 over the coefficient. And when you do that, that will essentially give you the right mole to mole relationship when you're doing these kinetics calculations of these rate expressions. So as we can see here, the coefficient of A is 2, taking 1 over the coefficient. A is still a reactant, which means we do need the negative, and that is to change the concentration of A over change of time. When we go to the product side, we do not need the negative. The coefficient is 1, so much like usually in chemistry, we don't write 1 over 1, right? Or we don't include the 1, but technically it's 1 over 1 is happening on the right-hand side, the change in the concentration of B over the change in time. In general, you can write a rate expression for a reaction by doing that formula right there, which is 1 over the coefficient, the change in the concentration of A over the change in time, negative 1 over the coefficient, change in concentration B over change in time, obviously negative here for both reactants. Then we have our positive as well. They are all equal to each other, and they all equal the average rate of the reaction. What this allows you to do is pretty much if you have just one piece of information, maybe you know how in this reaction C is changing with time, or maybe you know how D is changing with time, or A or B, or maybe you just know the average rate of this reaction. You could figure out how everybody else in the reaction is changing with time by using these relationships. So, for example, let's just say I was interested in C, but I knew how A was changing in time. So maybe it tells me A is changing, however A is changing. I could actually just pull out the rate expression for each of those. So if I were to write a rate expression for A, it would be the rate is equal to minus 1 over A, the change in the concentration of A over the change in time. I could also write one for C, which is the rate is equal to 1 over C, change the concentration of C over the change of time. Now, if I did know this information here, that would allow me to actually calculate the rate here. Now, that rate that you would calculate there is actually the same rate that you have down here because it's in the same reaction. So by just having that piece of information about A, I could then figure out the rate of the reaction, which would then allow me to solve for C, how it's changing with time. And now I know how C is changing with time. And then I could actually do it for everybody that's in this equation. So you could pull out just the two things you're maybe interested in and write two individual rate expressions, and basically, you're going to use one of the information that you have to basically figure out the rate, and then use that rate to relate it to everybody else in the equation. Again, this idea here, as we were talking about, is whenever you solve for this number, positive. This number here, if you were solving for how A is changing with time, you will end up with a negative number as it's a reactant and it's decreasing with time. If you were solving for this guy, which is the change in the concentration of C over the change in time, you will end up with a positive number as it's a product and it should be increasing with time. And again, by taking 1 over the coefficient, it sort of wraps the mole-to-mole stoichiometry calculation together with the kinetics calculation without having to maybe just kind of do them separately. By the way, you can do them separately if you want. You can just approach it like a stoichiometry problem to begin with and do the moles of whatever they gave you to the moles of what you're looking for, and then add in all the kinetic information at the end and do the calculations separately. And we'll come across one later on here where we'll show it both ways, but you could do it either way. But if you take 1 over that coefficient, that'll kind of help you out with the mole-to-mole relationship. Any questions on that? Yeah. Correct. So, like, for example, if you had this number, which would technically be this whole thing number, it would technically be negative. And that, again, is why we have the negative here in front of it, because that negative number that you would have and that negative front will then turn this rate into a positive number. And so that's again why the reactants have that negative in front of the expression to turn that number basically into a positive number because they're reactants, so they're decreasing with time, which means every time you do final minus initial, you're going to end up with a negative number. And that negative in front makes the overall rate positive. And that's also why we don't have one on the product side because they're increasing with time. So every time you take the difference between the final and the initial, you'll end up with a positive number, and that's good for the rate. Yeah. Other questions? All right, so why don't we write the rate expression for this reaction? So take a moment there and write up what the rate expression would be. All right, let's take a look and see. So here we're going to go, the rate is equal to coefficient here is 1. So we do need a negative because it's a reactant, it's decreasing with time. 1 over the coefficient here would basically be 1, so we don't really have to write it. Change in the concentration of CH4 over the change in time. That will equal our next reactant, which means we also need a negative because it's a reactant. Here the coefficient is 2, so we're going to go 1 over 2, change in the concentration of O2 over the change in time. Coming to our product side, coefficient is 1. We don't need a negative here because they're increasing with time. So this is basically just going to be the change in concentration of CO2 over the change of time. And lastly here, coefficient of 2, 1 over 2, change in the concentration of H2O over the change in time. Now you can put them all equal to each other. You could do like I did earlier if you didn't really need everybody here to do the calculation. Maybe you just needed methane and CO2, you could just write the 2 for those and just kind of go about your calculation. When you obviously have numbers, you would put in there and stuff like that. Yeah. Cool. If you're asking like you would do this part, or you're asking like you do if you had the numbers given to you individually, like the initial final concentration, like the initial time and final time, you would do that part first, and then basically you're just going to be dividing by 2, yeah, and then with a negative as well. Yeah. Other questions? All right, so why don't we try one with some numbers here and see how we do. For this reaction, if we have a initial concentration of for I minus, it goes from 1 molar to 0.868 molar in the first 10 seconds. What is the average rate for that reaction in 10 seconds? And what is the change in the concentration of H plus over the change of time? Here's the equation. So let's take a few moments there. Okay, let's take a look, see how we're doing. So again, here we're given some information, and we could try to figure out since we actually have numbers here. We definitely are given the initial concentration here of I minus, which is 1 molar. We call that I. We have our final concentration of I minus, which is 0.868 molar. And we're interested in H plus, and we have our time basically of 10 seconds. You could call that your final time, and your initial would obviously be 0 seconds, is sort of what we got going on. So in this particular case, we could write a rate expression for everybody that is in this reaction, but we're really not interested in like everybody in this reaction. So I'm just going to kind of break it up into kind of individual rate expressions for the two things we're interested in. Clearly, we got some information about I minus, so that's probably a good thing to write. So if I go to the equation for I minus, the rate is going to equal, here's I minus, it is a reactant, so it's going to be decreasing with time, so it needs the negative. Again, to take care of the stoichiometry, we do need to take 1 over the coefficient in this case. So 1 over 3, which is its coefficient. And again, that takes care of the mole-to-mole relationship of how this thing is reacting with everybody else in the equation. That's going to be the change in the concentration of I minus over the change in time. So that's our little rate expression for I minus. And again, we're picking it because obviously we have information given to us. The other thing that we want to figure out is really how the concentration of H plus is changing with time, which means we probably need a rate expression for that one as well. And if we write it for that one, the rate is equal to H plus here is still a reactant, so we will have a negative because it should be decreasing with time. The coefficient for H plus is 2, so we're going to go 1 over 2, which is the coefficient. And again, that's going to take care of the mole-to-mole relationship, the change in the concentration of H plus over the change in time. First off, any questions on those expressions there? Now, clearly, you could have done all of them equal to each other, right? But we really don't have to do anything with anybody else in the equation. So why kind of put them in there? But technically speaking, everybody's equal to the rate here, and they're all equal to each other, and that's how we can basically figure out how things are going on. So at this point, we're going to actually solve for the information that we have, which is basically this one here, since we do have the I minus given to us. So in this case, if we plug this in, the rate would equal minus 1 over 3. Remember the change in the concentration here, we want to do final minus initial. So we're going to go 0.868 minus 1 molar. And that's important, right? Because that's going to give us a negative number, right? To go with our negative out on the outside to turn our rate, as we were talking about, into a positive number. We could do 10 minus 0 seconds for our time. And if we pop all that into our calculator here, we're going to end up with a number. And that number is going to be 0.0044 molar seconds, by the way, is the average rate of this reaction. The units do not cancel, and that gives us the units of molarity over seconds, which obviously is a unit of rate. Any questions on that there? Uh, yeah, you probably should show it. If you don't, you'd probably be okay if you didn't, but you probably should get a habit of just kind of doing the final minus the initial, even if it's 0. Other questions? All right, so why is this important to us? Well, it's important to us because it's the problem we're doing now. It's important to us because ultimately we want to figure out this here from our second rate expression, right? So we have the rate is equal to minus 1 over 2, the change in the concentration of H to H plus, not 2, H plus. Gotta make that H plus maybe. Fix it. H plus over the change in time. So really what we're looking to solve for is this. And how the first part of the question here helps us is this rate is that rate, right? So by using that to figure out the average rate of the reaction, we now have the rate for the other guy because frankly they're in the same reaction, right? Which means they have the same average rate that's happening in that reaction. So now what we have is 0.0044 molar seconds is equal to minus 1 over 2, the change in the concentration of H plus over the change in time. Once again here, this is what we were really looking to solve for, which means to solve for this, I need to do what? I need to multiply 2 to the other side, but not just the 2. I also need to take the negative as well. I need to take the negative. So I got to multiply basically minus 2 to the other side. That will take care of that basically. And that will get us negative 0.0088 molar seconds is how H plus is changing with time. Yeah. So any questions on that? We see a couple of things, right? We solve for H plus, which is a reactant, and we did end up getting a negative value for how it's changing with time. And that makes sense because it should be decreasing with time. So we get a negative value for it. The H plus, is it moving at the same rate as the average reaction rate of the reaction? It is not. It is moving about twice as fast, right? And that is because the stoichiometry of H2 and that H plus in that one is 2. Yeah. So that's why you have to take into account the mole to mole relationship because things are not reacting in a 1-to-1 fashion. And this one's actually doing twice as fast as the average rate of the overall reaction in terms of what is given away. And again, that's what it can tell you. Clearly, if we want to know how everybody else in this reaction is changing, we could just continue to do similar calculations for everybody else that's there as well. And that's why this is really an interesting thing because all you need is just, again, one piece of information about the reaction, the average rate, how somebody is changing, and you can basically relate it to everybody else in the reaction and figure out how everybody is changing with time as well. Any questions on that there? Yeah. Why don't we try this one here? If we have 2.4 times 10 to the 2 grams of NOBr, the molar mass of NOBr is 109.91 grams. I'll throw the moles in there. Not sure where it went. If it decomposes in a 2 times 10 to the 2 milliliter flask in 5 minutes, find the average rate of Br2 production in molar seconds. So take a few moments there, work it out, see what you come up with. Okay, let's take a look here, see how you're doing. So in this case, we're not given sort of molarity and all that. We do need to probably calculate it, but we are given some information about NOBr. We got some grams and we got some molar mass given to us, and we do have some volume. So we definitely get to molarity from this. So since NOBr is involved, we'll write our little rate expression here. Rate's going to equal, once again, NOBr is a reactant, so we're going to go negative 1 over the coefficient. It's going to kind of do the stoichiometry wrapped together with the kinetics calculation. Our change in the concentration of NOBr over change in time. We are also looking for Br2, which is over here. So we can write a rate expression for that. The rate is equal to, it is a product, which means it should be positive with time and increasing with time. That is how much of this that's going to basically go through decomposition reaction, if that's reaction. No, because still in the equation is a reactant. So in this case, in order to make the NO and the Br2 that's on the product side, you need to decompose your NOBr, which means it has to be decreasing with time. And NO and Br2 here would be what would technically be increasing with time as it's being made as that process goes through. So with that, because BR2 is a product, it should be positive. We go 1 over the coefficient here, which is 1 over 1, which again, we don't really need to put in there unless you'd like to. That basically leaves us with the change in the concentration of BR2 over the change in time. So since the brackets there are concentration, I'm going to figure out the molarity here of our NOBR. So my NOBR is our grams, which is 2.4 times 10 to the 2 grams. We'll use our molar mass here, and we're going to really divide by the molar mass so that the grams cancel. Obviously, if it was not given to you, you would need to go to the periodic table there and calculate it yourself. And that would be 2.4 to the 2 or 240 divided by 109.91. Going to get you like a 2.1836. I'm going to take it to a few digits here, moles of NOBR. Now, this is in the brackets molarity, which is again moles per liter. I do have my liters here, which is 2.0 times 10 to the 2 milliliters, 1,000 milliliters in a liter in that case. So basically, take 200 and divide it by 1,000. That is going to get us 0.2 liters. That is what we're going to divide that by. Right? And in this particular case, that will get us 0.2. That's going to get us a 10.918 molar. That is technically right there, right? What's going into that deal. This is going to happen over 5 minutes. Since I want my final answer here to be in seconds, I am going to convert the minutes into seconds up front, so I don't have to worry about it later and be in minutes. So 5 minutes in this case, converted to seconds. 1 minute is 60 seconds equals 300 seconds. And now I have really the bottom part. This is essentially 0 to 300 seconds is basically what we're looking at here. Now, when I put it in there, I have everything I need to figure out the rate. So the rate's going to equal minus 1 over 2. That's going to be a negative 10.918 molar divided by 0.2 liter. No, not 2, 300 seconds there on the bottom would be our time. Not that. We already did that. 300 seconds will be good. By the way, why did I make it negative? Because it is a reactant, which means if we technically had all the individual information to do final minus initial, it would end up as a negative number. And that negative, along with this negative, again, going to turn us into a positive value there for the rate, which is what we need in this particular case. So, sometimes they may not give it to you in a form where, you get the negative, but you have to kind of remember that. And if we do that, they're basically going to take that divided by 300, also going to divide it by 2. That's going to give us an average rate here of 0.0182, again, molar seconds, as none of the units cancel out. Any questions on that so far? Yeah. Yeah, well, it does depend if you sort of let the reaction run to completion, it would be pretty close to zero. It may not always be, it depends, if you don't let it go all the way. And even if you let it go all the way, it may not completely use up everything that's there at that point, but most of it will be gone. Yeah. Other questions? All right, so really we're using this to help us out to figure out how BR2 is changing with time. And as we wrote earlier up there on top, the rate is equal to the change in the concentration of BR2 over the change in time, which means now that we know the rate, we could pop it right into there. And basically that equals, in this case, the same number. Right? And again, it is a product, so it is increasing with time. First off, any questions on that? So just to demonstrate, as I was mentioning earlier, when we do 1 over the coefficient, again, that is sort of wrapping the stoichiometry into the kinetics calculation. if you wanted to kind of do those things separately, you could. And just to show you, if you were going to do this problem, kind of keep those things separately, you really should end up with the same answer. So I'll just kind of put a little line around here. So if we were to kind of take just like the stoichiometry part of it first, which we know obviously in this case we have NOBR given to us, but eventually we want to get to BR2, we could see from the equation that again for every 2 moles of NOBR, we get 1 mole of BR2. So that is the mole to mole relationship, just like you were doing regular stoichiometry. We would actually start this problem pretty much like normal. We would do this calculation and we would get our moles. And picking up with those moles, I would take 2.1836 moles of NOBR. And now I'm just going to do just a basic stoichiometry process where I'm going to use my mole to mole relationship. 2 moles of NOBR is going to give me 1 mole of not H, BR2, BR2 in that case. And if I do that, we'll go 2.1836 divided by 2. That's going to get us 1.0918 moles of BR2. Now that we have the moles of BR2, we could just kind of put in all the rest of the information. We could take our moles of BR2, and since it's in the same container, it obviously will have the same volume, which is 0.2 liters. And we could turn that into molarity, which will give us 5.459 molar. And we're looking for a rate, which means we can divide this now by our time, which was 300 seconds. And if we do that there, we now end up with the exact same answer, obviously, as we did before. And you're just kind of doing them separately, the stoichiometry part, and then kind of roll in all the kinetics sort of part of it with the rate expression at the end. And you can see you get the same answer, and that's perfectly okay if you would like to do it that way. The other way, it does just sort of kind of wrap it together. You know, this is why we have that 1 over the coefficient right there, right? 1 over 2, right? Is basically what it's doing when you take 1 over the coefficient is that mole to mole relationship for you. Questions on that there? Oh, it's the same one, I think. Yep. All right, questions on rate expression. Now, let's talk about some factors that do affect the rate of the reaction. So, obviously, the nature of the reactants has a big effect on how fast or slow the reaction may take place. If you have small molecules, they do tend to react faster than larger molecules. Gases react faster than liquids because gases have a lot of energy. They're constantly flying around, which means they're most likely going to come across somebody else pretty quickly because they're moving around. And by the way, they have enough energy to get up and over the hill to the other side when they collide in terms of the energy component of it. Liquids will react faster than solids. So liquids have less energy, obviously, than gases, but they still have a lot more energy than solids, right? And that's why liquids are fluid because they still have enough energy to move around each other, right? And that's why it's still fluid in the liquid state, as opposed to in the solid state, they kind of lock themselves in because they don't have enough energy to continue to kind of move around each other. If you have a powdered solid, is more reactive than a block solid, more surface area for things to react on. Certain metals, certain chemicals are more reactive than other. That activity series, maybe you learned about when you did single replacement reactions, right? You got like hydrogen in the middle and a bunch of elements on top and elements on the bottom, and anybody higher on the list is more reactive than anybody lower on the list. Ions are also a lot react faster than molecules. If you're not sure where you find ions in a solution floating around. That's where you find ions. They are floating around in that solution. So they're ready to go, essentially. They don't need anything to happen for them to be able to react. Temperature is a really big factor on the rate of reaction. If you increase the temperature, typically you increase the rate of the reaction. Vice versa, if you lower the temperature or decrease the temperature, you oftentimes will slow down the reaction. A lot of reactions, if you just pop it up about 10 degrees Celsius, they will double the rate. And there's a relationship we'll talk about in this chapter is known as the Arrhenius equation, which deals with the rate, constant, and changes in temperature. Catalysts are important aspects to typically speed up a chemical reaction. A catalyst is not a reactant. Again, it's not a product, and it does not get used up in the reaction. It is there typically just to speed up a reaction. Uh, that's usually what people are talking about when they talk about catalysts. There are some catalysts that actually will slow down a reaction, but I would say probably 99 times out of 100, somebody's talking about catalysts or talking about it as sort of speeding up the chemical reaction. We typically find catalysts a lot of times written on the arrow, like platinum, H plus, like an acid as a catalyst. What they're able to do is find a more efficient way for that reaction to take place rather than the normal way of we're just going to hope that somebody comes in contact with each other as they're moving around. And that could be something as simple as maybe you got gas molecules flying around and you put a solid in there, and these gas molecules are attracted to the solid. That then puts those gas molecules very close to one another, and that's going to increase the rate at which they're going to react rather than them just kind of flying around hoping to run into each other and stuff like that. Sometimes the environment's really important, which is why acids and bases sometimes are used as catalysts. Sometimes you do need like an acidic environment for things to be more reactive, or maybe a basic environment for things to be more reactive. As we'll talk a little bit about at the end, catalysts can be homogeneous, which means they're in the same phase of whatever is reacting, like a homogeneous mixture. Things are the same throughout. Everybody's in the gas phase, everybody's in the liquid phase or solid phase. Heterogeneous, they're in different phases. Concentration is a big effect on how fast or slow a reaction takes place. The larger the concentration, the faster the reaction takes place. If we look at the true definition of molarity, which is moles of solute per liter of solution, as you hopefully know, a solution is made up of two things. It is made up of the solute, which is the smaller part, and that is the stuff that you dissolve in the larger part of the solution, which is the solvent, and that's the larger part. And it is the solute molecules that are reacting when you have a solution, is those guys floating around the solution. That is what is reacting. So if you have a large concentration, that means you have a lot of solute molecules in that solution, for example, and that's going to probably help you out pretty greatly because again, they're not going to have to go travel very far to find somebody to react with because there's a lot of them in the solution to begin with. um, Concentration of gases does depend on the partial pressures of the gas. The higher the pressure, the higher the concentration. As you may remember, as pressure goes up, what happens to volume? Goes down, right? Our friend Boyle's law, right? So if you have higher pressure, you also will have probably a smaller volume, which puts those gas molecules again closer to one another and going to allow them to react probably a little bit faster. Do you have a question? Correct. It basically stays unchanged, in the reaction and stuff like that. So it will be there at the beginning, it'll be there at the end, and again, it's just really there to sort of facilitate the reaction occurring faster. Yes. An example of catalyst is like, for example, platinum metal is an example of that. In certain reactions, you use a piece of platinum, and like I said, in some reactions, maybe it's a gas, and those gas molecules are attracted to the metal, and that allows them to get together and react faster. And at the end, the metal is still there. Nothing really happens to the metal or something like that. Um, Magnesium dioxide is sometimes used in a reaction, decomposition reaction of potassium chlorate, and that is there. It's just like a react not really a reactant, but a substance that helps initiate the reaction occurring a lot more efficiently, and it will still be sort of there at the end of the reaction as well. Other questions? Okay, so Concentration again depends on that ratio. And again, the larger the value of the concentration or molarity, more solute molecules, lower the concentration, then obviously you have less solute molecules in there. So that brings us to the rate law. And the rate law is a little bit different than the rate expression. And one of the differences is when we're dealing with the rate law, we are not all that interested in products. It's all about reactants. So if we have this equation here, or this reaction here, we could write a rate law for it as you see there, the K times the concentration of A to the X and B to the Y. So as I mentioned just a second ago, it is all about reactants only when you're doing rate laws. So no products are involved in the rate law. This is the rate of the reaction as we kind of been talking about, as we talked a little bit about earlier today. That is the rate constant. That is that value that essentially will remain constant for the reaction at that particular temperature as you're doing it. These are the concentrations of both reactants. Now, X and Y, these are what are known as orders. And X is the order with respect to A, and Y is the order with respect to B. And you could actually calculate the overall order of the reaction by simply adding them together. So if you were to add those guys together and take X plus Y, that'll give you the overall order of that particular reaction. We'll talk about different orders a little bit later on in the chapter. Now, rate laws are pretty much found experimentally. Orders are found experimentally. The orders, the X and the Y, are not the coefficients in the balanced equation. So they are not the coefficients in the balanced equation. That is not how you get those. You do get them through calculation that we're going to talk about, and you'll have some experimental information typically given to you. So what does the rate law sort of help us understand, and you know, what can it tell us? So for example, let's just say that we had a reaction and we did it where the concentration of A was 2 molar and the concentration of B was 2 molar, right? And we did an experiment where we did this. And if we were to put this in to our rate law of the rate is equal to K times A times B. And let's just say that in this particular example, we know that A and B's orders are 1. So much like usually in chemistry, we don't write the ones, but I'll just put them there. Each of these orders for A and B are 1 from individually. Overall, this reaction would be what's known as second order. By adding 1 and 1 together gives you 2, or second order. And if we put in our values in here, we would get a rate, for example, of, and I'm not going to worry about this number since it's a constant value. It's going to be the same number no matter which one I do the calculation. So I'm just going to kind of ignore what that is. This is the constant. I'm going to put that in and get 2 basically times 2. And that will essentially give me 4 molar seconds. This is a rate. I'll add the seconds in and all that. Now, let's just say I did this reaction and I go, dude, this reaction was like maybe too fast or this reaction was too slow. And I decided, well, maybe I want to play with this reaction to see if I can maybe speed it up or make it slower. So let's just say in this case, I decided I'm going to double B's concentration. I'm going to leave the A concentration alone and do this experiment again. And I'm going to roll with A still at 2 molar, but I'm going to decide to I'm going to double the concentration of B the second time around. So when I put it into this rate law, I'm going to end up with the rate is times 4, which means my rate is 8 molar seconds. What happened when I doubled the concentration of B in this case? My rate went up by a factor of 2, right? I doubled it. So if I wanted to slow down this reaction, did I just do it? No, I made it worse for myself. I'm going to have to move a lot faster and loud because this reaction is going to be over a lot quicker, right? So that's not going to help me. So maybe I decide, okay, I'm going to go back to my original. Instead of doubling B, I'm going to like cut B in half. And if we do this reaction again, and we cut B in half, we end up with 1 molar, and we put it in there. We got the rate is equal to 2 times 1, which gives me 2 molar seconds. And in this case, did I slow down my reaction? I did. Now I slowed it down by changing the concentrations of one of the reactants. I could also, if I wanted to, change A's concentration up or down, and it would have a similar effect. And that's what the orders in this case sort of have an effect on, is like the proportion of each of those reactants that you need to kind of get yourself a specific rate to occur. Now, let's just say here to finish up on that, in this reaction, maybe the order for A was 1, and maybe B was a second order, and it was kind of a different reaction, and this was second order. By the way, the overall order of this reaction would be what? 2 plus 1 is 3, third order reaction by just adding those overall. Now, let's take our first set of deals here with the 2 and the 2. And if I put that in there, I will end up with 2, and now that's 2 squared. That's going to give me 4 times 2, which is 8 molar seconds. So now my rate of this reaction, even though I'm using the same concentration as the first one, is actually moving twice as fast as the first reaction, because the order of B is now second order, right? So it's actually moving faster. So now if I do the same change of, I want to now change my B to 4 molar in this case, I'm going to pop that into my rate, and now I got 2 times 4 squared. That's 16 times 2. That's a lot of math. Is that 32? I hope molar seconds. So now by doubling my concentration of B, my rate went up by a factor of what? It was originally 8. It's now at 32. That's a factor of 4. Yeah. So by doubling in this reaction, I now increase my rate by a factor of 4, when my order for B is 2 versus when my order of B was 1, right? By doubling in the first situation, I was only able to kind of increase the rate by a factor of 2, right? Versus a factor of 4. So in this case, we could see that between A and B, which one would have the greater effect on the rate of the reaction? It would be B in this case, right? Now, if I want to increase the rate of this reaction, but not as fast, I could then change the concentration of A and leave B alone, right? It would still cause an increase, but not as big of an increase, because in this case, A is only first order. I'll be right with you on your question. So if I did that and I did A as 4 molar and kept B at the original 2 molar and put it in here, I would end up with the rate is equal to 4 times 2 squared. 2 squared is 4. 4 times 4 is 16 molar seconds. So now by increasing A in this case, I got an increase in my rate, right, from my original, but is not up to 32 times. It's only 16 in this case, and it went up by a factor of 2 rather than 4, right? So you could see in this case, if you wanted a really big uh, change in your reaction, is going to be B in this case. That would make a big thing because its order is second order. If you wanted a slower sort of change, you could change A and it would cause a slower effect. Question or? No, so the squaring here, as we'll talk about, is coming from the experimental information for this reaction. And in this second example, we're just saying it happened to be second order. And that would be determined by doing some calculations that we'll talk about next time as to what the orders are. And they're not just given to you from the equation. You don't just randomly square them or something like that, but they're based on the experiment that you did and what the orders would end up being.